This is our EC535 final project, which is a predictive maintenance and data logger for Industry 2.0. It runs on a BeagleBone, collecting machine simulated data at two rates: high frequency for on-device machine learning training and low frequency for long-term cloud storage via AWS. We also simulate and implement predictive analytics and machine learning to predict machine failures before that they happen. Here's our real-time dashboard updated live. It can be monitored over an SSH connection without being locally present. Since the data collector is on a VPN, you can see all the timestamps, temperature, pressure, everything that we're collecting from the simulator. We also see like the mode, configuration files, all this kind of important information. One thing you'll see on the real device is the current probability threshold as a percentage. So that's just for monitoring, and then when it reaches over the threshold, that's when you get an alert that a failure is imminent, and it will fire off an email alert to maintain the machine, take the machine down, in order to reduce like a unplanned downtime of the machine. You have to keep that monitor. In order to collect the high frequency data, you just echo 1 into the capture file, which starts collecting in a new folder for training data, high frequency, which is all defined in the config file. This should be collected at the same frequency that the machine spits out data. So our machine sim is 100 hertz, so you can train with as much data as possible. You can imagine that our CSV is only a few data points, but in real life, there could be tens or hundreds of data points being ingested for this process. We don't really want that much data saved all the time, as it's wasteful and pointless to save 100 data points a second. But for machine learning training, that may be something we want, so that's why you're able to turn it on and off. We locally buffer all the data points, as we found that the BeagleBone is kind of unreliable on the Ethernet. And we upload with a 5-minute cron job that scans the logs and the train folder for CSV files for the low and the high data frequency data sets, and upload and delete the local copy. This way, if the device loses its connection, data collection continues without interruption. We're sending here to an AWS S3 bucket with Bodo3.
So the next step is to use machine learning to predict machine failures. For this, we use the basic random forest classifier model and train it on the CSV data from the Python machine simulator. We went ahead with this model because it works well with the limited and mixed data we are working with. The model can predict if a failure in the machine is about to occur about 20 seconds in advance, and sends an email notification when the probability of an imminent failure is greater than 70%. Right now, the model is not the most accurate, but it does a pretty good job in notifying a failure most often than not. Improving the ML bit might be a scope for improvement in the future.
So for deploying the project here, we're just compiling the primary binary that we wrote in plain C with the Open 62541 library that's used for OPC UA polling. The main thing is that data points that we're polling specifically are actually hard-coded into the binary. They're not configurable at runtime. But the rest of the configuration is configurable at runtime with all these parameters that can be safely changed, including the frequency of the primary loop. So the primary polling loop, we pull at the largest frequency, the highest frequency, and then use modulo to sample down to a lower rate in the main loop for the lower frequency collection. And we rotate the log files when it passes the max log file size. So each file is the same size when we upload to AWS. The core of our project is the predictive maintenance with machine learning. So that's learning to forecast the equipment failure before it happens. We're able to predict using our simulated data set on the injection molding machine we're simulating. So instead of reactive repairs, our model can read the data, learn the failure patterns we programmed, and send an alert to machine operators, buying them valuable time to shut down the machine, replace a part before the critical failure takes place. And we're doing it all while saving on cloud costs and ensuring high equipment uptime and lowering unnecessary maintenance and increasing safety.